Okay, let's get started. So my name is, no, I think this will be fine. My name is Lars Peter Clausen. I work for Analog Devices. And this talk will be about the industrial I/O, the Linux industrial I/O framework called IIO, and how you can use it or leverage it in the context of SDR. And let me quickly start with what is actually IIO. So it's a framework in the Linux kernel. It was, well, it handles pretty much all non-human interface input and output devices. So the name says industrial I/O, but it's really, because we have in the Linux kernel, we have the input framework, which handles human interface input. So we had to come up with a different name for this framework. So it's called industrial I/O, but it really handles all kinds of sensors. There are ADCs, DACs, light sensors, accelerometers. Recently, we merged some sensors, which I know you call like lifestyle sensors, which like you have in mobile phones, which count how many steps you take or how many calories you burn. So it's a very diverse set of sensors that are supported by this framework. It has been in the upstream Linux kernel since version 2.6.32, since 2009. And it was originally developed by a guy called Jonathan Cameron. He developed this as part at the university as part of a research project. So he had lots of sensors and he needed a common framework to represent these sensors. So he came up with this framework, and at some point it was merged in the upstream kernel. Initially in the staging area of the kernel, so that's where all the kind of work in progress stuff goes. But we moved out of staging and released 3.5 2 years ago, or almost 3 years ago now. And as of today, there are drivers for about, well, there are 200 different drivers, but each driver typically supports more than one device. So we have like, I don't know, 500, 600 devices that are supported. And the next question is, of course, what else? What does this have to do with SDR? Or why should we use this for SDR? And what the I/O framework defines is a common lower level API which abstracts away the hardware, the actual register access to the hardware. So you get a common API or ABI that you can develop your applications against. And I think we've seen this in some of the talks before. The first thing you actually do when you start working on the SDR project is you write some code to actually get the data out of your device. And in my opinion, that shouldn't be the way it should be, because if you have a common framework which provides the capabilities of getting the data out of the device, you can actually focus on writing your solution, on your actual application, without having to care about all the low-level register access. Because lots of the modern devices which are used for software-defined radio can be quite complex, like over 1,000 registers, and you need to know how to program all these different registers. And this is where the I/O framework comes in. So we do have a driver for a certain part, and this driver exposes a common API, and this API is shared between different kinds of devices. So you can write an application once, and hopefully it will work with like this chip, this chip, this chip, without you having to actually modify your application at all. And another advantage of IIO is that it's actually running in the Linux kernel itself. So we get all these kinds of things like interrupts, we get memory mapped interface registers, which are sometimes not so easy to handle if you just have like a user space application. And the other thing that IIO provides is a fast and efficient data transport, both for transmitting data from an application to the hardware, as well as transmitting or capturing data from the hardware to the application. And something that we're working on that we hope to have ready in a couple of months is using the VM splice and splice syscalls of the Linux kernel to directly be able to stream data from the ADC or somewhere else to the network device without having to copy it first into a buffer in a user space application and then back copy it into a buffer in a network device. So you basically have zero copy, which allows like fast and efficient ways to store your data or send it out over the network without having lots of CPU overhead. And so what I'm trying to do in this talk is give an overview of the I/O framework in the context of software-defined radio. It's not going to be a complete overview of the I/O framework. There are other talks that go a bit more into detail. I've linked them at the end of the slides, so if anybody is interested in it, you can look up these presentations. And what you have in I/O as the starting point kind of is the device. That's the main entry point. So if you have a physical device, typically you get a I/O device as a corresponding structure, software structure, which you can reference and work with. You don't always have to exactly a one-to-one mapping. Like if you have one physical hardware device, but this implements two logical functions, you would typically register two I/O devices, one for each function. And these I/O devices are represented in sysfs. Does everybody know what sysfs is? Who doesn't know what sysfs is? Okay, a few people. So sysfs is, I can actually show you. Oh, well, will show you later. But it's basically a virtual file system provided by the Linux kernel, which is exposed to user space, which you can access with normal file open close system calls. You can read and write from it, and this is what used by the I/O framework for configuration of devices. So the next thing we have is we have attributes. One device can have many attributes, as many attributes as it wants, and the attributes are responsible for two things mainly. One is describing the capabilities of the device, and the other is allowing to configure the device. Configuring is pretty easy. You have a file, you can open the file, you can write a new configuration to it. Like, let's say we have sample rate. You can, if you want to change the sample rate, you open up the file, write a new sample rate to the file. And capabilities come basically in two flavors. If you know that there's a file that allows you to change the sample rate, you know that this device has, well, the capability to somehow change the sample rate. And there are also some files. For example, let's say you have a discrete set of sample rates that's only supported, then you will have a file called sample rates _available, which will list the discrete sets of sample rates available. So your application knows which sample rates are available or which capabilities the hardware has. The next thing we have is channels. And again, a channel, so there can be multiple channels per device, and there can be multiple attributes per channel. And similar as the device represents the physical hardware, the channel typically represents a physical channel. Like on an ADC, you have an input voltage channel. On a DAC, you have an output voltage channel. On an accelerometer, you have acceleration channels, input acceleration channels. And so a channel has a direction, either input or output. It has a type, which can be many different things. It can be voltage, it can be acceleration, it can be energy, it can be, as I said earlier, steps, like steps you've walked. In addition, there's an index. If you have multiple channels of the same type, you will want to have an index, channel 1, channel 0, channel 2, and so on. And what's also possible is to assign a modifier, which you use if channels are, if you have like multiple channels but which are kind of corresponding. For example, in an accelerometer, you typically have 3 axes, and the way you would represent is not 3 different channels, but not using different indices. You would say it's still channel 0, but you would say this is the X channel, Y channel, and Z channel. And for example, in a software-defined radio context, that would be you have one data stream, one data channel, but it has an I component and a Q component, and that would be then a modifier. Again, attributes. There are a couple of standardized attributes, for example, scale and offset. So what the type The type also specifies is the unit in which the data that's coming through the data channel is in. Like for new channel types, we typically try to use the SI units. But for example, for some legacy stuff like voltage, we use microvolts. And what you don't want to do in your kernel driver is you don't want to convert each and every sample, especially if you are running at a high sample rate. So we provide a scale and the offset attribute which you can use to convert from the raw sample you have to something known in a known unit. But there are also lots of other different. So basically everything that can be configurable in a channel can be an attribute, like the calibration data or filter settings or hysteresis and so on and so on and so on. The next thing we have is a buffer. And again, the buffer can have attributes. But per device, there can actually be only one buffer at most, either 0 or 1 buffers. And the buffers also reference the channels defined earlier. And what the buffer allows you to do is gives you access to the data. It's represented as a def, as a character device. It's a normal character device exposed by the Linux kernel. You can read and write from it using the normal read and write functions. For buffers, if you are running a device in buffered mode, the channel will describe what kind of data or the data format that the channel is in, like 16 bits, unsigned, little endian, big endian. So your application actually knows what the payload data is and can interpret it accordingly, and you don't need to hard code this into your application. Again, the buffer is configured using DisFS files. Typically, you will have like a length of the buffer or the size of the buffer and whether the buffer is enabled or not. But in theory, it's possible to have all kinds of different attributes for buffers. The IO framework supports different buffer implementations. So the easiest is, of course, you have a device-specific buffer, but we rarely need this. There's one software-based buffer, which is the FIFO. And this is mainly used for slower sampling applications, sensors which sample like in, I don't know, 100 hertz or something, or in the kilohertz range. When you get an interrupt, when the sample is ready, then read the sample from the hardware and write it into your buffer. And then the user space application eventually wakes up and can read from the buffer. But of course, this is not going to work in the SDR context where we have mega samples per second. You can't have one interrupt per sample if you are running multiple mega samples per second. So for this, we have DMA buffers. And the way DMA buffers work is you essentially have you have a DMA controller, which is used to copy data from your converter into memory region. And you can use mmap to map this memory region into your application, which means you don't have to do a copy, so it's zero copy again. And well, this allows us high speed and low overhead transport. And the way it works is that we allocate small chunks of data, so-called blocks. And the block is basically allocated by the application, certain size, the amount of data you want. And then you pass the ownership of the block to the incoming queue of the hardware. And this then goes on to a DMA controller. The DMA controller reads the data from a pipeline, from your processing pipeline, from your receiver or transmitter pipeline. And once it's done with the block, once the block is fully filled up, it puts it into the outgoing queue, and user space can read from it. So you really only move around meta information about where the data is and what length the data has, but you don't actually copy the data itself, well, which allows for very efficient access. And so the user space application can sleep on this one, or so this one is blocking. That means you can use normal syscalls like poll or select and put your application to sleep. And once the DMA controller is done processing it, the block, the application will wake up and then can run its analysis algorithm on it and once it's done with running the algorithm, it will give it back to the DMA controller. And typically you will have a couple of blocks, like 3 or 4, to keep this pipeline fully saturated all the time. And one interesting bit is you can dynamically allocate and free these blocks, which means, for example, if you have an algorithm which wakes for beacon frame, for wake up frame or whatever, you can allocate a large buffer and send it to the DMA controller, and your application only wakes up occasionally. And then once you find this wake up frame, you want to have smaller blocks to have a lower latency for, well, low latency processing. So you will allocate smaller blocks and pass these smaller blocks into the DMA controller, and you, well, have lower latency data transfer. So to put this into context, I'm going to use the example of the FMCOMS2 EBZ, which is a board we designed which used the 89361, which I think is also on the ATIS B200 and 210. It's basically an integrated chip for software-defined radio or software-defined radio applications. It's this one over here. It's tunable from 200 kilohertz. So the sample rate is tunable from 200 kilohertz up to 56 megahertz, and the bandwidth itself is, so the base frequency is tunable from 70 megahertz up to 6 gigahertz. It's full duplex, MIMO 2RX, 2x. And the way, so this is just this board, and there's just a chip on this board, and you typically hook it up to FPGA using the FMC connector. And this is kind of the system overview diagram. This is the chip itself, has 2 DACs, 2 ADCs, and so on and so on. Then we stream the data over into the FPGA, and we have a small processing pipeline by default, which just does some correction and calibration data, and then sends it to a DMA controller, one for transmit and one for receive. That's what we've seen earlier. And the way this is represented in the sysfs is you have one directory which is called sysbus.io devices, in which you have all the different devices. And as you can see, in this case, we have 5 devices. 2 of them are just normal sensors which do temperature, and so this is the X-ADC and the Xilinx FPGA, which is used for voltage and temperature monitoring. This is a temperature and voltage monitoring chip that we have on the FMCOMS2 board, but this is the device which corresponds to the 89361, and this is the device that responds to the receive DMA block. And this is the one that corresponds to the transmit DMA block. And so let's quickly take a look at how this looks like for the device. So this is the 89361 device, and this is what I was talking about earlier. You have channels in voltage, and the channels have all kinds of different attributes. What you can see is if a certain kind of attribute is shared between all instances of the channels, you don't have this index. And if it's channel specific, you will have the index like 0, 1, 2, and so on. So these can be changed per channel, and these can only be changed per direction. So you're using the same RF bandwidth for all channels, but you can change the gain individually on the channel. Output is similar. So these are not all the attributes. It's just an overview because there are way too many. And there are also some device-specific attributes like the FEAR filter can be loaded, and we also have a temperature sensor. This is the capture device, and as I said earlier, our pipeline is really simple. In the example case, there's only a couple of attributes which can be used for calibration or basically calibration of the channel. But what we have is a buffer subdirectory, which corresponds to the buffer, and a scan element subdirectory. And the buffer subdirectory basically just has an enable and the length specifies the size of your buffer, and the enable specifies if it's enabled or not. And for the scan elements, you will have for each channel 3 attributes. One is called enable, which specifies if the channel should be currently enabled or not. So you can disable certain channels if you don't want to capture them. There's an index, and this index is unique to the channel, and it tells you in which order the channels are stored in the hardware buffer. So let's say this one has index 0 and this one has index 1. Then we know if both are enabled, this one will be in the buffer before this one. If only this one is enabled, if this one is disabled and only this one is enabled, there will only be one channel in the buffer. And there's also the type attribute, which contains, as said earlier, information about the layout of the channel and the buffer, like the storage size, how many bits it will take up, how many significant bits it has, if it's shifted, like it's a shift, if there are, whether there are non-significant bits at the bottom, whether it's little endian, whether it's big endian, and these kinds of things. So you can use this to reconstruct the buffer layout and don't have to know about the specific chip that's going to send data. So this was the kernel layer, the kernel framework, and now we're going to talk about the plumbing layer that sits above the kernel, which runs in user space. And in user space we have a so-called libIO, which you can kind of think of like our libAlsa, like you have a libAlsa for the ALSA framework, which provides a bit higher interface. So when you write an application, you don't want to necessarily deal with all these sysfs files. And what the libIO does is it reads the sysfs information about the device and the channel from sysfs, and builds it into data structures, into C data structures that your application can use and work with, so you don't have to do any raw access to the sysfs. And one other thing is that it transparently handles the difference between so-called low-speed and high-speed devices. And the difference, as I explained earlier, is that the low-speed devices use this buffer, and you use read and write to get data from or to the buffer. And with a high-speed interface, you would normally use mmap. And libIO will automatically use mmap if it's available, and otherwise fall back to the slow-speed interface. Another thing that libIO provides is it has internally an abstraction layer itself, which allows it to have multiple backends. And one backend is the local backend, which will directly talk to the sysfs files. But a different backend is a network backend. So we have a daemon, which you can run on a board. And on your laptop or on your high processing power computing platform, you can run your application, specify, okay, my hardware runs on this board, which is IP address, and the application will behave the same, whether it's running directly on the hardware or on a remote platform, on a desktop PC or on a laptop PC or on a server in a data center. And there's also a debug plugin which allows you to simulate real hardware and test things without actually having access to real hardware. We do have Pythons. We have bindings for different programming languages like Python, C#, and C++ works also because the library itself is written in C. And the library is cross-platform. Of course, the local backend only works on Linux, but for example, the network backend works on Windows and Linux, and also on other POSIX-compliant operating systems. So the network backend is, hopefully written POSIX-compliant. So it should work on the BSDs or on Apple OS. It's called macOS. So as I said earlier, we have a network backend, and we have IOD, which is a daemon which runs on the board where you have your physical hardware, and it's the server for the network backend. So you connect to the IOD via the network backend. And one thing the IOD also allows is multiplexing different applications. So you have two applications accessing the same hardware. The IOD will take care of making sure that the superset of enabled channels from all applications is enabled in hardware. So you can actually get all the hardware that, all the channels that, all the data that you want, without having to make, without the applications conflicting with each other. So if you run two applications, both on the local backend, one will turn the channel on and the next one will turn the channel off, and strange things will happen. And if you use the IOD, you don't have this problem. And of course, also there's the advantage that you don't need low-level system privileges to access the device anymore. And this is basically just a diagram of how it works. So you have the I/O devices here in the kernel, and the libIO with its local backend and the network backend. And the IOD uses the libIO itself, using a local backend to access the hardware. And then on a remote machine, you can also use the libIO, but the network backend talks to the IOD server. The IOD server talks to the local backend, which talks to the hardware. And similar, so this application running here and this application running here can actually be the same application. And the only thing you need to specify when you run the application, okay, well, use the IO local backend or the remote backend. And I'm kind of running out of time, so I'm going to skip this. And we also have a GNU Radio plugin, which is kind of interesting from a software-defined radio perspective. We have two basic blocks or classes. One is the IO thing, the other one is the IO source, which each subclass, the basic source or basic thing. So they allow you to stream data from an IO device into GNU Radio or transmit data to IO device from GNU Radio. And it's also possible to subclass these devices. And we have two examples of this specifically for this board, which allow you to expose some extra parameters. And there should have been a live demo, but we're pretty much out of time. So only going to explain what I was going to do is we have our high-tech FM radio antenna. We have the 89361. We have the FPGA on a Z board connected to my laptop via Ethernet, and on my laptop is running GNU Radio. And as you can see, no, you can't see. Let me just quickly pull this over. We have a really simple pipeline implemented here, which uses the FMCOMS2 source and sends it into a FM radio receiver and then an audio sync. And if we run this, anybody knows a good FM radio station?
532.375 megahertz.
103.7. Which one?
103.7.
103.7. Should be it? No, 101.
While we're doing this, if you leave the room, please
And
take
there's
trash with you.
radio. And that's it.